Okay, so I realize I have lied to you. That was actually not the last video. This is the last video because it's part 2. So we're going to do a circuit diagram example. So I drew out, let me go back one. So I drew out a battery. This is our symbol for a battery. And anytime you see a line like this, so this right here, that's just a wire. That's just connecting all the parts together. This little device right there, that's our resistor. So that's anything that we would plug in to a wall or an outlet or something. This little guy right here, that's a lamp. So that's technically another resistor, but we commonly use lamps in our diagrams. And then the bottom, all of this mess here, all of that's just wires. So there's a basic, very simple circuit diagram. What I have at the top here, that is our voltmeter. So this is how I'm going to measure voltage. And what you normally do is you measure the voltage across something. So remember we said that voltage was this idea of a difference in pressure, a difference in electrical pressure. And again, I'm doing this in quotes on my hands right now because that's not really what it is, but this is how we're going to try to understand it. There's a difference in voltage from this point here to this point here. So when the current goes all the way through this wire and then it goes through this resistor, that means it loses some voltage from this battery. So if this battery right here was 10 volts, then after you get past this resistor, it's going to use some of those volts. So let's say it used, I don't know, 5 volts. Then that means when we get to this lamp is only going to get to use 5 volts. If that was totally over your head, that's okay. We're going to do a concrete example later. This is an ammeter, and this is what measures current. And the ammeter is measuring current that goes through it. Remember, so current is something that flows through things. So we need to connect it this way. And it's going to measure the current going this way at this point. So there's our battery, there's our lamp, there's our ammeter, there's our voltmeter, then there's a resistor. And then let's throw in this. This is a switch. And so this is an important concept. If the circuit is not complete, if you cannot draw your finger away from the battery following the wire and go all the way through the circuit and all the way through the parts and go back to the battery, then the circuit will do nothing. Nothing's going to happen. So a switch is a way to basically turn on and off a circuit. So right now, nothing will happen to the circuit. That lamp will not be lit. There will be nothing going across that resistor, nothing through the ammeter, and so on. So we have to use that switch and connect it, and then it will work. So here's a dumb example. Here is a circuit that's just a battery and a lamp, and that's all it is. So right now, the lamp is off, or the light is off. There's no current going into that. It's getting no voltage, nothing. It's just a lamp unplugged. And then as soon as I close the circuit, then the light will turn on because the circuit will be closed. Let's talk about an idea called power. And this is really a topic of energy, and the reason I didn't really do this before is because it doesn't really come up that often except when you talk about circuits. So you may have heard like a 60-watt light bulb, that's power. So power is just the rate at which work is done. So it's how quickly the energy changes. So in other words, power, P, is work, W, divided by the time. So it's the rate at which work is done. So, or the change in energy over time. These are equivalent statements. They are the same thing. Because remember, work equals a change in energy. They are the same. So it's going to have these units of joules per second. So how many joules of energy get used every second? And that is defined as a watt. So joules per second will be watts. And this is the idea of power. Now volts, they are defined as work over charge. So how much energy does it take to stuff a bunch of charge into something so that we have a difference? And so if you think about it, it makes sense. You have a bunch of charge that's stored in a battery, and the volts that are in there is how much energy does it take to put that charge in there. So the more energy it takes to put in there, the more volts that you're going to get. So those are going to be joules per coulomb. And since power is work over time, and up here we have volts equal work over charge, we can resolve that for, we can resolve this for VQ equals work and make a substitution in here, or in this case QV, same thing, and that divided by the time. Now, if you look at that, you might recognize something. You have Q over T. Now that's the current. So this is just charge per second. So then our equation for power in terms of a circuit is power equals current times voltage. Or in other words, P equals IV. So your two equations to remember, or two of the simple ones, I like to think of them as PIV and VIR. So P equals IV and V equals IR. These will be used very commonly in our circuit diagrams. So let's do an example with a circuit diagram. We have a 1.5 volt battery and one resistor of 10 ohms. What is its current? So what is the current? If I took a measurement of any point in this circuit, what would be its current? And that's what we're going to find. So it's simple. We're just going to use VIR. So we're going to divide our voltage by our resistance, and that's going to be 0.15 amps. So this is more typical of an actual circuit. Usually do not have really high currents in small electronic devices. Now we're going to learn about what we're going to have to deal with if we have a more complicated circuit like this. Because circuits aren't just a battery and a thing, and that's it. A lot of times what you do is you combine things. If you've ever worked on a construction site, or if you worked on building houses, you realize that the wiring is a bit more complicated than just a power source and a thing, and then it connects back to the power source. You connect a lot of things together. Or if you think about over the holidays and you think of the Christmas tree, sometimes if one of the lights goes out, then they all go out. And that's because if you break one of those lights, what you're doing is you're breaking one of those resistors, and then there's no current that goes through it. But we're going to talk about two ways to connect things. One is called series, and then one is called parallel. So series means that you have resistors that go in a row. Parallel means that the wires will split apart, and they'll go into two paths. So series and parallel, let's compare and contrast. Series means there's one path to follow. Parallel means that there are several paths you can follow. So think of a fork in the road instead of just on a one-way street. And then in series, the current is the same everywhere. So if I found the current through one resistor, it's going to be the same current through another resistor. Because think of it as a bunch of cars on the highway. And if there's one slow car in the front, everybody goes the same speed. And parallel is a bit different. So current changes at a junction. So if you think all of a sudden the lanes open up, then everybody can go a different speed because nothing is really holding you back anymore. So you're free to go at different speeds. But we'll talk about how exactly that works in a circuit. So a basic example, two resistors in a row, all connected in a row, would be series. And then on the right we have a wire right here, and it splits off into two wires. And then you have a resistor in each. So in this one, the current just goes to the right, and it goes the same for everybody. In parallel, however, instead of it just going to the right, think of it as going into this little point here, and then it splits off into two different currents. So one of them goes up and one of them goes down. Alright, and we mentioned this a little bit before, but I'll touch on it again. Voltage drops, there will be a voltage drop across each resistor. So as you have the charges flow through this circuit, some of the voltage will get used here at V1. So some of the voltage from the battery will get used up on that resistor, then the rest of it will get used up on this one. And then if you add up both of those drops in voltages, if you measured those, it would equal the total voltage, or whatever the battery was. If you look at parallel, you can measure the voltage across both of them, and it turns out it has this weird property that they are actually the same. So if you took the voltage across the top one versus the voltage across the bottom one, they would be exactly the same. So the same voltage. So what that means is, for Ohm's law to be true, that means the current has to be a little bit different. So here is a series circuit. Here's a quick example. All the resistors are connected in a row. They just go from the battery into one resistor, into the next resistor, and into the next one, and then it goes back to the battery. However, if we have a parallel circuit, then all of it leaves the battery, and then at one point it goes down this path, or some of it goes down this path, some of it goes down this path, and some of it goes down that path. So we'll have 3 different paths, and then they all meet back up and combine again here. Then you'll have times where you have both series and parallel. So if you look at right here, these 2 right here are in series, and then the rest are all in parallel, and this should be connected. That's connected right there. So we'll learn how to tackle a combination circuit like this one. Okay, now the way to tackle these problems is you have to think about how the resistors are set up. So in series, we can find the current if we add up the total amount of resistance, because it's the same amount of current everywhere. So the same current goes through all 3 of them. So what we need to do is find the total resistance. And the total resistance in series is very easy. You just add them all together, and that's your total. On your formula sheet, it will look a little like that. But all this means is the sum of all of the resistors. So however many resistors you have, add them all up. Then if we have a circuit like this one, this is parallel, all 3 of them are parallel, they behave a bit differently. And it's given by this equation. So this might not be as intuitive, and that's okay. This is why I'm just giving this relationship to you. So to find the total resistance, you add the inverses of all of them, and then take the inverse. So if you think about what numbers you can put in there, it's not really going to equal the total resistance, as in if you had 3 1-ohm resistors. Or never mind. Forget I was saying that. We're going to do an example in a little bit. This is our relationship for resistors in parallel. Or also written on your formula sheet, it's like this. But don't get confused too much with this notation. It just means add up all of the inverse resistors and then take the inverse. Okay, so let's do a real example. We've got 3 resistors in series. 10 ohms, 5 ohms, and 3 ohms. So their total resistance is just going to be 10 ohms plus 5 ohms plus 3 ohms. So then their total resistance for the entire circuit is going to be 18. And this total here, I should write this right here, this R sub t that I'm writing is commonly referred to as equivalent. Dang it. Equivalent resistance. Okay, so you might hear this terminology, but don't let it confuse you too much. This just means what is the total resistance of the circuit, and that's all that is. Alright, so moving on. Now, let's do an example with the same 3 resistors so that you can see the difference. I have the same exact 3 resistors, but I'm going to get a different amount of resistance in the end. I've got 10 ohms, 5 ohms, 3 ohms, but remember we add them up differently. So we add up the inverses. 1 over 10 ohms plus 1 over 5 ohms plus 1 over 3 ohms, and then I take the inverse of this number, because this answer, 0.633 repeating, that is 1 over the resistance. So if we take the inverse of that, we're going to get 1.58 ohms. So that's a little bit weird. I have a 10 ohm resistor, 5 ohm resistor, and a 3 ohm resistor, and the total resistance, if it's configured this way, is less than all of them. And that's because they are put in parallel, so they behave a little bit differently in terms of current. Alright, now let's do an example with both. Or actually, let's talk about the voltage again. So when measuring voltage, remember we go across. So we measure across something. So we're going to put our voltmeter, we're going to put it around a resistor. And with current, you have to measure through it. So you basically stick it in the circuit. So it needs to go through. Okay, so this is what voltage would look like. Our voltmeter, it's going to be measuring across this. So you'd put the two wires around the resistor to measure the voltage. And then same thing over here. If you wanted to measure across either one, because they would be the same, you would measure it across the resistor. Then, if we want to do the current, you have to stick it in the circuit like this, because remember, we want to know what flows through it. Or if we wanted the current here, we'd want to see what flows through it. Alright, now here's an example with real numbers, and then we're going to wrap up with this. So we got a 12-volt battery, and then we have 3 different resistors. 2 of them are in parallel, and then 1 is in series with the other 2 parallel. And what we'll do to find out the current in all of them, the current through each resistor, we have to start by finding the total resistance. And we start by finding the equivalent resistance of those 2 in parallel, and then add it to the 4 ohm resistor. So these are in parallel, and then that one is in series with those 2. So we start by finding the equivalent resistance of 3 and 6. Okay, so then when we do that, we can redraw our circuit like this. Because we've basically found the total resistance of that parallel component, and then we can plug it in here. So 1 over the each resistor, and then take the inverse, will give us that question mark. So 1 over 3 plus 1 over 6, take the inverse, we're going to get 2 ohms. So then 2 ohms plus 4 ohms is the total resistance of the circuit, the entire circuit. So 4 plus 2, 6. So our total is 6 ohms. So the current that leaves the battery is going to be 12 volts divided by 6 ohms. So 2 amps. 2 amps is coming out of here. So now let's look back at the original circuit. We have our 3 resistors, and that means 2 amps is going through the very first resistor. So it's going to go right through the 4 ohm resistor. So I can figure out how much voltage goes away because I have the current. Oops, I didn't want to erase that. I have the current and I have the resistance. So I can find the voltage that gets used up here. So we can find the voltage across this resistor. So it's going to be the current times the resistance. 2 times 4 is 8. So we used up 8 volts in this first part. Alright, so if we started with 12 volts, we went through the 4 ohm resistor, we lost 8 volts. That means we only have 4 volts that go across this other section. So V2 across the 3 ohm and 6 ohm resistor is only going to be 4 volts. Right there. So this is how we can figure out the current that goes through each one. Because we know they both use up 4 volts simultaneously. So that means they're going to have a different amount of current that goes through each one. So the current that goes through the 3 ohm resistor is 4 volts divided by 3 ohms. So it's 4/3 of an amp. So you notice the current goes down a lot. So it's no longer 2 amps, it's less current. And then we can do the same thing for the 6 ohm. So it has still 6 volts. Oh no, not 6 volts. That's supposed to be 4. That's supposed to be 4 volts. So 4 volts. 4 volts over 6 ohms. So the current that goes through it is not going to be 1. I don't know why I wrote that. It's not going to be 1. It's going to be 4 divided by 6. So 4/6 of an ohm, or 2/3. So 2/3 of an amp. All right. So we said that there's 2/3 of an amp in the bottom, and then there were 4/3 in the top. So that means we have a total of 6/3 amperes when it comes back out and they recombine, which is 2 amps. So we had 2 amps coming right out of the circuit. We're going to have 2 amps coming right into the circuit. But as we go through this part and this part, the amperage will go down, because that 2 amps has to get split into 2 parts, and that's why. Okay, so that is the end of this video. We're going to do a simulation in class where we're going to test all of this so you can verify that all of this stuff is actually true.